Here is our continuation of optics dynamics. We're looking at the reflected and transmitted fields, and we already looked at the incident field. So just to recap, the blue here is the wavefront position. You can think of it as a peak. Associated is the information of the electric field in orange, and green is the direction of the wave vector k. Now let's just look at the algebra for the reflected wave. There's a vector amplitude here, which is an amplitude times a unit vector pointing in the orange direction. And we have kr and r. This is our plane. As we saw, everything on that plane has the same form. And kr is equal to the magnitude of kr times this unit vector. And you can see that we can resolve it into two components. There's the horizontal one, and that's going to involve sine theta. So we're going to see that when we take the dot product later on, kr sine theta r times z, and that's exactly what we saw, is that the kr times sine theta is going to be the horizontal component of k, and that we saw arising in Snell's law. We now see that the x component, which is going this way, pointing up, is in the negative x direction, so we have minus cos theta r. We could do the same for the transmitted wave, so we'd have the magnitude of k transmitted, and then plus, because the waves are going in increasing x and increasing z. And of course, the k value will be the k associated with this index of refraction. We also see that the h fields are all coming out of the page, and that's going to make the algebra much simpler because we also have to calculate the h. So the plan is to summarize all the relations we have on the next panel and then compute h. After doing that, we then need to do the boundary matching of the horizontal, the tangential components of the electric and magnetic vectors E and H.